6x congruent to 1 modulo 7. I want to now solve this equation for x. Just to remember from before, this has a solution because 6 and 7 are relatively prime. Seven is prime. That's nice, but it's not essential. It's not necessary. As long as the two are relatively prime, I can solve an equation like this. Why would I want to solve an equation like this? Well, the reason is because whatever I find for the x in this equation will be the multiplicative inverse of 6 mod 7. This is very useful because then if I know the multiplicative inverse of 6 modulo 7, I can solve any equation like 6x congruent to anything modulo 7. Just like how with normal algebra, if I have an equation 6x equals 5, I just divide by 6. So it's very useful to know how to divide by 6. How do I do this? Well, at the beginning, if we don't know any special method, we can still use brute force. We can just try everything. You remember, there is some way to take 6 times something, and it will be 1 mod 7. We could try 6 times 0. 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, and 6 times 6. And I can see what all of them are, mod 7. I know for certain that one of these will work. We proved that before because that's how we drew our pictures. Before, our pictures would have things like this. 6 times 2 is 12, and 12 mod 7 was 5. So before, we used to draw a picture which would have 2, an arrow meaning times 6, and it would go to 5. So we know from before that because 6 and 7 are relatively prime, I will get everything in this column exactly once. And I could try to do this. 6 times 0 is 0. 6 times 1 is 6. And as you can see, I will be finished at some point. It could take a very long time, but we can try anyway. 6 times 3 is 18. 18 modulo 7 is 4. 6 times 4 is 24. Modulo 7, remainder is 3. Looks a little bit strange. How come these are going 0, 6, 5, 4, 3? If you see a pattern, especially with modular arithmetic, there's a very good chance that the pattern will continue and that there's a reason for the pattern. It seems like what's happening is I am just reducing by 1 every time. But that is because if I take from 6 times 4 to 6 times 5, this step, what am I doing? I'm doing plus 6. But if I go modulo 7, 6 and minus 1 are the same thing. That's why every single one of these looks like it went with minus 1. And so I can finish. This goes to 3, 2, and 1. And that shows me that 6 is actually its own multiplicative inverse, modulo 7. This is interesting. Something is its own multiplicative inverse, modulo 7. Let me dig a little bit deeper into this. This is like an equation, x squared equals 1. Think about normal algebra. Something times itself equals 1. Normal algebra, let me just use z. How many solutions does this have? It has 2 solutions. One of the solutions is z equals plus 1, and the other solution is z equals minus 1. These are solutions in the normal numbers. But if you think about this, since this is true in the normal numbers, it's also true that this is true modulo anything. This means that if I take minus 1 squared, it's always equal to 1. And also, minus 1 squared is therefore congruent to 1 mod anything. I can write any number here, like 24, because their difference is 0. That's divisible by everything. What that means is that whenever I have minus 1, its multiplicative inverse is going to be minus 1. So, minus 1 has multiplicative inverse of minus 1 modulo anything. This means that when I looked at my original problem, in my original problem, I had here that I could take 6 times 6. But when I looked at the original problem, really the trick in this question was to look all the way at the beginning and say, well, 6 is just minus 1. How hard is it to find x now? Well, minus 1, so x is also minus 1. And that's the quickest way to solve this question. I wanted to show all these different ways to solve, because first, we can appreciate how difficult it is to do this without any special methods. We are lucky that it was only modulo 7. If we were doing this modulo 7001, I might have to make a very, very, very long list and check. It could take a long time. We need to find a faster way to do that kind of question. For that, we'll go to the next lesson.